And then let's go back. So last example in the field of vehicle dynamics, I promise, is just because, of course, we come from that field, so we have more examples there. But let's go back to our original. We said we can use a hierarchical trajectory planning and control framework to perform autonomous racing at the end. So we had a look at this block so far. So the vehicle dynamics block, how we can learn the vehicle dynamics from data and physics priors. Then in general, we have a trajectory planning module that basically plans the trajectories over a certain prediction horizon that can be very long to anticipate the corners and the upcoming behavior of the other opponents. Yeah, then, okay, in this case, we're also formulating some model structure neural networks for this module, but we don't want to present it here. Here, we want to directly jump to how we actually execute the planned trajectories, right? So this is the trajectory planner. Then we have a trajectory control module, in particular a feed-forward and feedback modules. Let's have a look at the feed-forward steering controller. So the one that really needs to steer the car to execute the planned maneuvers. So here, indeed, we want to output the steering angle. We call it delta. And we have as input some future predicted desired trajectories, planned by our high-level planner that tells us, okay, this is maybe the minimum time maneuver in this case. So we have the speed profile over a certain horizon. We have the acceleration profile over a certain horizon. So speed Vx, accelerations Ax and Ay, longitudinal lateral. Maybe also the vertical acceleration if we are on a 3D road. So we have this information in the future, right? So when we learn the dynamics, we typically look at the past history of what the vehicle did in the past or what the system did, and we try to predict the next time step. In this case, we can anticipate the future because maybe we have a high-level planner that tells us the desired future will look like this. So we can incorporate this information in the design of the controller that basically has the task to execute, to make the desired future become reality, actually. And so here we started from a baseline controller, which is, if you want, a heuristic, partly physics-based controller that computes the steering angle as a function of some quantities. Basically, we have a kinematic, nothing really special, like a combination of stuff, yeah, of kinematic steering angle. Very simply, an understeering correction, like, okay, we know the vehicle may steer in a certain way, we want to correct for that, a slight compensation for the longitudinal dynamics, and then some offset terms. This one actually went quite well, yeah, with this controller we won the 2024 edition of the Abu Dhabi Autonomous Racing League. So it was actually performing quite well, yeah, but we understood there were some limitations. By the way, yeah, on a full-scale car. We understood there were some limitations, like the performance we could reach was not really the best. So we could not really push to the upper limits. And so we said, okay, let's try to apply the idea of model structure neural networks to this use case. And even in this case, okay, yeah, we had two variants of our design. One that was basically conceived for the pure lateral dynamics, so no influence of the longitudinal dynamics on the lateral one, and then an extended version, which we said, no, let's consider also the influence of the longitudinal dynamics. So what happens when I brake or accelerate with my car and I steer simultaneously? And here the idea, the intuition behind, it's more or less like the last example we've seen. We do not start from the Newton equations in this case, but we start from, I mean, we could start from the Newton equations and reach a final design in that way. But in this case, let's not start from Newton. Let's start from another physical intuition that we have, which is another diagram, which is called the handling diagram, okay, technically. And it simply shows you how the vehicle is steering. Like if this diagram was a perfect horizontal line, then it would mean the vehicle would steer as we expect. Basically, it would be a neutral vehicle, a kinematic vehicle, perfect kinematic vehicle So basically, when you steer at low speed, you're expecting your car to steer kinematically, like your steering angle is proportional to the yaw rate of the car. It's directly proportional to the yaw rate. So basically, the more you steer, the more the vehicle is going to turn. But in practice, it's not always like that. Yeah, in this case, you see the vehicle is actually understeering, we say, so it steers less than what you expect. And this diagram is simply showing how much the vehicle is under or oversteering. And oh, yeah, welcome. Yeah, of course. Thank you. And indeed, so we can incorporate this idea without too much knowledge, extra knowledge, but we know that this diagram exists. Okay, its shape can be hard to model. In general, its shape can be very, very different from a race car to another, from an urban car to another. But we know it depends on the lateral acceleration, for example. So one idea can be, again, neural compositional modules. So basically, we want to say we have some local approximation of this diagram in a neighborhood of a certain region of the lateral acceleration, and have in general our neural compositional module to autonomously learn the shape of the diagram. An alternative would be to fit the diagram with the polynomials, whatever, but it's never so easy to do that, because with polynomials you also risk having at the end oscillations if you have higher degrees, and in principle things may not be so easy. So this is what we propose. So using basically a combination of local models in a neural compositional module that basically learns the shape of the diagram with some additional information. So, for example, we know, or we may assume, that the vehicle behaves symmetrically for left and right turns. And so for this reason, we use basically the absolute value here to activate the local models with the absolute value of AY, which is our lateral acceleration. And also in the design of the local modules, we are basically using a local linear model in this case. So we're saying, please use local linearized modules to approximate the diagram. But we have, so K1 and K2 are basically the learnable parameters. And here we have the sign of the lateral acceleration because we want to preserve the symmetry, again, of the diagram. In this case, in this way, we can also use fewer parameters, fewer learnable parameters, because we only need to basically to write, to learn the parameters that fit the right part of the diagram, and it will also be fitting the left part, but we only have one set of parameters, right? We don't have two sets of parameters for the right and for the left. And this is another correction term, which we know needs to be there from the physics. And basically, this is the shape of the activation functions phi that we use. Again, we choose the piecewise triangular because our scheduling variable AY is continuous. And we want, of course, the sum of all the functions to be always equal to 1 in order not to create an imbalance among the modules. Yeah, and this is basically the shape we choose. But then another physical intuition is that the shape, or a physical observation, is that the shape of this diagram, so basically this was the shape of the diagram for a certain velocity. Let's say all the points were collected at a velocity of 80 kilometers per hour. But what happens when the velocity changes? Well, the shape of the diagram is also changing quite a lot, or can also be changing. These are real world data in which you see how the shape of the diagram is actually changing with speed. But in this model, you see we're not considering at all the speed dependency. But we can do that quite easily. We can add a Vx velocity dependency. So we can say these parameters are actually not constant coefficients, they're actually functions of the velocity. But still we preserve, for example, the symmetry with respect to AY. We preserve at the end the linearity with respect to AY, to the lateral acceleration. So this is a simple extension we can plug in again based on some simple physical considerations. And okay, so this is the case we get, right, in which we have the local model, the local neural compositional module that depends on AY and VX. We're simply reporting it here. Then it turns out, so basically up to now, we're learning the quasi-steady state, right? We're learning this diagram is also a quasi-steady state diagram, so we don't see the transient dynamics there. It's only a static diagram, okay? Nothing about the transient evolution. And it turns out, in the most general case, you don't just have AY and VX, but if your vehicle is also accelerating or braking, you need to also consider AX, so the longitudinal acceleration, inside the local modules, so inside the neural compositional modules. So there we add AX. We also add AZ in the most general case, so the vertical acceleration. Okay, it's something more technical. And in this case, okay, I'm not reporting the model here, but these GYK input functions, okay, these are the input functions of our neural compositional module. They were actually designed from a local approximation of a physics-based vehicle model. So there we actually plugged in again the equations, the Newton equations, and designed local approximations of that model around some quasi-steady state conditions in terms of these four variables. Sorry. So again, this can be combinations of physics insights, the handling diagram we've seen before, plus some integration of Newton equations if you have them. In this case, we have them, so we can reuse them. And this was the quasi-steady state part. And then, of course, we have the transient part, yeah. And as we said yesterday, maybe for the transient part, we don't have so much to add in the design. I mean, we had, but it would be a lot more complex. And so, yeah, let's simply consider that the transient response, this is something we know, we can observe from the physics equations, but also from observed values. The transient dynamics depends on the velocity and the longitudinal acceleration. And so we can simply have some other neural compositional modules here that basically take as input the quasi-steady state part, which we've seen before, right? This G module, this G neural compositional module, we now plug it here. And then we can have another part that basically learns the transient dynamics. And again, here we want to have the dependency on velocity and acceleration because we know it from physics. We know the transient dynamics will depend on velocity and accelerations. And so each of these fully connected layers or finite impulse response layers will be learning the dynamics in different regions, in different overlapping regions of velocity and acceleration. And at the end, we sum, okay, of course, the outputs of all the modules. We can also have an output function here if you want, if you have some output nonlinearity. Like in this case, we want to basically learn the nonlinearity between the steering wheel angle and the steering angle at the ground, the floor. So this other module can be a more general purpose network if you want that learns this static nonlinearity, output nonlinearity. Right. So yes, this structure, if you want, it resembles the one we've seen yesterday for the dynamics learning part. Yeah, it's very similar. The only difference is that, or I mean, conceptually, we still have two neural compositional modules, one for the steady state, one for the transient. Here we have actually some future windows, yeah, some windows of input values in the future, because they are the ones planned by our planner. While yesterday we had some past windows, yeah, because we didn't know the past in our dynamic, we didn't know the future in our dynamics learning. Of course, we can also observe the past, but in this case, it's a controller, so we can assume we know the desired future from our planner, and we can try to reuse the future desired information in the controller.
Yeah, what I want to add is thanks to the fact that you are generating the instantaneous controller delta from the future estimation of the future trajectory that you estimate from the planner, you can take into account delays in the steering angle. Okay, so if your steering system have some delays, because you want to, because you know what must be the trajectory in the future, you can take into account and anticipate the steering needs. And so, yeah, this is a good thing with respect, for example, if you take this and then you use a more feedback controller, okay? Because this is a feed forward controller, you can anticipate the steering angle and compensate some delays inside the steering system. Okay,
Yes.
so this is something. Then, as you remember, you had also a feedback controller, no? In this
Yes,
case,
exactly. Yeah, here we're not showing, but this is the feed forward part, and then there's also the feedback part. Yes.
Yeah, but in the end, they had also a feedback part. But yeah, what is interesting that this kind of controller can compensate delays. Okay.
Yes, indeed. And you see actually the delays. Okay, so here probably I don't have the plot, but if you look at the again at the finite impulse response layers in their trained values, if you see an exponential, well, in this case it should be an exponential decrease, yeah, because probably the present is more important than the future. If we don't have dead times or delays, then maybe the trained weights of these finite impulse response layers have a decreasing. Right, they start maybe high and then they go down. They have a decreasing trend because the present information becomes more important than the future. But instead, if you have delays or dead times in your system because maybe your steering actuator has a delay or a dead time, whatever, then you observe that maybe the future becomes more important than the present. Yeah. So in that case, you can tell this from looking at the trained weights of these fully connected.
You can have also an estimation of what can be your delay or that.
Yes. So maybe in that case you have a peak. Yeah, maybe you start low with the values, then you go up, and then you go down again, right? Because maybe you have a peak in between because one of the future values, maybe after 0.2 seconds in the future, becomes the most important, and then it means that your system has a dead time of 0.2 seconds. Yeah. Questions here?
Also that
Yeah.
We in this case in this work we split the two. Probably looking at what we said so far, probably you can also join together in one single, and you increase probably the number of finite inputs response, and you get probably
so
the same
in only one neural computer module.
Yeah, probably is not so different.
Yes.
Yeah.
Yes, indeed. Yeah. Here we wanted to also keep the interpretability that one neural compositional module was going to learn the steady state, and the other one the transient. But in principle, you can also merge them if you find another way.
Yeah.
It's still possible.
The only thing probably is that in this case you have here you have the activation are in velocity and longitudinal acceleration, but here you have another two activation variable, and so the number of finite inputs or bombs will increase now because you
it will probably increase. Yes. But in principle, the design is flexible, of course, and also the Model-E library lets you actually play around with this quite easily. So we actually benchmarked this controller against a general purpose network. So a one in which basically we use the same inputs. We concatenate them along the same dimension, and then we feed everything to a two-layer neural network, multi-layer perceptron, if you want, with an LU activation function, exponential linear unit. Okay, it's just one type of activation function. And then we used another baseline, and then the heuristic based the steering controller that I was showing at the beginning, that basically won the 2024 edition of the race. Which was this one. And yeah, these are indeed some nice videos of the car traveling on the track in Yas Marina in Abu Dhabi. And basically we use these telemetries, so the recording telemetries of the car racing in Yas Marina to train our controller. And basically the interesting thing is we can train our controller with even one lap, only one lap of telemetries of real world data, or even less than one lap. So basically, you see here we have actually different training sets. The small, yeah, exactly. With the three sectors of the track. Yeah, this is the track on which we are racing. And okay, in this case, we're of course racing alone. So in one case, in the case of the small training set, we only use the third sector. Here, the one in yellow, to train our controller. In the medium set, we're using the first and third sector, and then the large training set. It's not really large, but it just means it contains the full track, yeah, the full lap. And
the validation we use the third sector.
Yes, and in the validation we use actually the data from another lab, in which probably we were driving even faster or slower. I don't remember, but it's different data. And let's see what happens. Yeah, this video actually it's nice because it was at the sunset, so it still looks nice. So what happens is with the large training set, our controller, the last one in green, is still outperforming all the benchmarks. Yeah, the general purpose one neural network, a baseline from our model structured and the heuristic controller. We outperform both in training and validation. But the interesting thing is when you use a small training set or a medium, but especially the small one, small training set, basically here you see a lot of difference between our controller, the model structured one, and the general purpose network, especially on the unseen validation data. You see here it outperforms quite significantly in terms of RMSE. So 0.3 against 0.1 basically.
So the fraction of variance
explains. Yes, and also the fraction of variance and explains. So we're able to capture both the accuracy with the RMSE, and the FVU tells us the scatter, the dispersion. So how much we can, how much variance we can actually explain in the data. And this is interesting because it means with this type of models, we can afford to use smaller training data sets without losing too much accuracy and still be able to generalize on unseen data. While, of course, with general purpose networks, you can perform in principle very well, but you tend to need, of course, a bit more data if you want to generalize well on unseen scenarios, yeah? Questions up to now? Yeah? Otherwise, we can have a short look at the code, even for this one. Just very shortly, but just to let you know that, okay, this model was actually more complex, yeah? So also the code, of course, can be a bit longer, but in principle, it's just putting together the things we defined. So basically, we will have our inputs here, the inputs of our model, so velocity, accelerations, longitudinal, lateral. Okay, in this case, we use also the curvature as an input, but it's just we can obtain it from AY, so it's not a big problem. And then the output will be our steering angle. We can define some constants if we have them. Here we're just loading the data and computing some maximum values to later normalize maybe the data. Here we want to say, okay, please use 10 samples in our feedforward windows. Yeah, so in the windows, in these feedforward windows, please use 10 values in the future. And then here again, we say what is the number of local models or channels that we want for each of the variables. So for the lateral acceleration, we want to have, which appears here, we want to have 5 channels for AY. The centers of these activation functions, we can also say what are the values of their centers, yeah? In this case, we just want to have a lean space, yeah, so an equal spacing of the centers from 0 to the maximum value of AY. The number of channels for the velocity. So in this case, maybe 3 channels are enough, one for low speed, one for medium, one for high speeds, because indeed our dynamics changes, yeah, as a function of the speed. For the acceleration, the same, maybe 3 channels are enough. These are all hyperparameters that we tune. Maybe in this case, we want to have one channel that is exactly modeling the dynamics for AX equals 0. And then the other ones, so one for negative acceleration, one for positive acceleration. But that's just a choice. Yeah, that's just because we want to have one model that captures the dynamics when the vehicle is not accelerating, yeah, basically. And then, okay, computing some initial guesses. If we want, we can normalize some variables. In this case, we're also saturating the inputs. This is a safety measure. So because, of course, here we have some inputs at the end. And in principle, okay, we may also not saturate, but then if we see something at deployment time that goes out of the maximum value seen during training, in principle, our model is still outputting something reasonable. It's not outputting something fancy, but since we then have to go on a real car, we want to be maybe a bit more conservative and decide that we want to saturate, so we cannot extrapolate badly, essentially. And you can do this simply with parametric functions. And parametric functions is simply a way to define your own function. In this case, we define a saturation function, which is very simply a min-max of x between a minimum and a max value.
Want to spend a word on this? This is a way where you can incorporate just a simple PyTorch inside your code. So if you not find what you want, the model idea was to have the possibility to include new function, and you can create this parametric function for taking into account this.
So you can simply reuse the torch math functions, whatever. It's still supported, yeah. So the tool is of course in Python and supports PyTorch, based on PyTorch. So also for the absolute value function, we use the abs from PyTorch and so on. And indeed, yeah, so we can define our own parametric functions. This can be also very complex. Yeah, I mean, also for the local models that we find here, we basically use parametric functions to define their formulation.
The other thing is related to the fuzzy. You use the syntax to apply the center, but also you can define the range and the number of center. So in principle, you could avoid the code that is upstairs. Because you can say just 3 center, 10 center in this range, and this is performed automatically.
Indeed, yeah. So here we define the activation functions appearing here in the steady state, and then in the transient parts with the fuzzify command. We say we want to have triangular functions that take as input the absolute value of AY saturated or of AX and so on with their centers. And look here, okay, we want the inputs to be in the future in this case, yeah, we said. So we want them to be from the current time step into the future. And so what we do here, we want to take as input of our saturation functions, for example, the lateral acceleration dot SW, so dot sample window. Yeah, we select a sample window for the input. And the sample window in this case goes in the future. So this would be the number of time steps in the past, right? And this would be the number of time steps in the future. So we have 0 time steps in the past. So we start from the present time step and we move into the future by this number, which is equal to 10. Yeah, is the one we defined before. Yes, so this is a simple way to define a
and this is window. This information is used during the creation of the data set. So when the CSV of the data is loaded, is the framework taken into account to take and create the windows that you need for training. So
yes, so indeed
you change these numbers, then you load the data again, and you have a new data set is compliant with this range.
So we don't need to create then the windows of future data manually. Yeah, if you do this in Keras or in TensorFlow, you need to create the windows manually. This is done basically internally by the framework. You just need to tell the framework what is the sample window you want, and then it's done. Yes, indeed, the activation functions, again, for the other variables. Here we're defining also the shape of the local models. Yeah, we want to have a certain function to model the handling diagram locally, as we've said, with the local linear models, but also then the Vx dependency and also Ax dependency. So in this case, it's more involved, the formulation.
And then you create.
Yes, and then yeah, we create the local model for the handling diagram. So it's basically this one. So we have an input function. In this case, we have no output function. We only have the input function, which will be the handling diagram generator, which we have here. Okay, so this tells us how to define the local models. What are the inputs at the end for this one? So it's inputs and the activation functions with their shape. Yes, yeah, exactly. Yeah, same thing then for the transient dynamics. Yeah, we define the activation functions. We pass them to the local models. In this case, yeah, of course, we have only output functions. Yeah, we don't have input functions here. So the output function is a finite impulse response layer, which we define here again with an exponential initial guess, because that's what we expect.
Yeah,
and the game is done.
Monotonicity decrease. To say that
Yes.
it must be the opposite of the standard. Normally,
So yes,
is based that you are doing a past window in the default is past window, and so you take an increasing monotonicity. In this case, you set as decreasing because
yes,
you are going from the from now to the future. So
yes, so it's still an exponential initial guess, but we say it's not an increasing; it's a decreasing exponential, just because here we have future time windows. Yeah. Yes, and then yeah, indeed, our transient dynamics takes as input the output of the handling diagram part. So of this part here is taken as input to the transient dynamics together with its own activation functions. And then the output is simply, the overall output is simply the output here of the, or the output here of the transient dynamic part. Yes, very, very simply like that. Then we add the model, of course, and we add our loss function, and the game is done. And then we neuralize the model. Here you see all the values of the constants and parameters that you may have defined with their numerical values. So you also see all the functions, Fuzzyfy activations with their own initial guesses. If you provided an initial guess, you see everything here. Yes, exactly. This can be very long, yeah, because in this case, the model is very complex, a lot of models. This is probably the most complex models we ever created, yeah, or one of the most complex, yeah.
One big one was when we joined the forward dynamics plus the...
Yes, indeed, yeah.
Yeah, the control.
But in principle, yeah, you can build models with arbitrary complexity, yes. Okay, I would say we can go back to here and maybe conclude this part. Stop the sharing.
Hai sbagliato, hai stoppato lo sharing di...
Ah, yes, sorry. Yes. Okay. Should see the correct one. Yeah.
Okay, yeah.
Yes, indeed. So this was the training. And before seeing the next example, which is a simpler example, yeah, don't worry, it's not so complex. Let's see, it's more a methodological example. Yeah, let's see a methodological example, which I think is interesting for many of you. Because here we want to say, in general, yeah, not only in autonomous racing, but can we actually yeah, indeed, boost the closed loop performance of a controller from limited data. So in other words, can we also adapt, if you want, the controller to changing conditions without also without collecting data, actually? So can we do it end to end in a somehow unsupervised way by reusing a simulation model which we may have? But let's see more practically what we mean. Yeah. So boosting controller performance is the goal here. And okay, let's see how we can do that. So in general, you may have a model structure neural network or another type of neural network or even physics-based model that simulates your dynamics. Okay, so given some inputs, given a past window of input, so this can be in the form of a neural compositional module, past window of inputs, then you get your output at the end. Yeah. So maybe you have steering wheel and pedals. In the output, you have the trajectory, for example. And then you have your controller. Your controller does the opposite, right? So the controller wants to give you the input at the end using, as we said, maybe a future desired window, a future maneuver that you want to track, somehow. So a future window of output, and maybe your measured output for the current time step. You want to have the corresponding input to execute your plan. Right? And now the question is, can we somehow train the controller, or can we let the controller learn to control the simulator autonomously somehow by interaction in closed loop with the simulator? Okay, so either we pre-train the controller, that's fine. That's what we showed before with our autonomous race car. We pre-train the controller with the collected closed loop data, that's fine. But here we want to say, can we let the controller learn on its own to control the plant? Okay, something different. So in other words, we can start, okay, we can do it in 2 steps. Step 1 is train the simulator. Okay, so the orange block, we train the simulator with supervised learning from collected real world data, if we have it. So we train it, step 1. And then step two, we couple the controller and the simulator, right? So the simulator is not anymore a standalone block, but it receives the input U from the controller. So the last control input becomes the one computed by the controller. And then the output, or the predicted output, if you want, because this is a simulator model, it's not a real world physical system. So the predicted output is then fed back to the controller, and this is used as a real measurement, right? So this is the current state of the system, if you want, the current measurement of the system. And then we still have our desired output. It's the desired output then goes to the controller, and it will be computing the corresponding inputs to be fed to the plant and back again. So now we can train the controller in closed loop with a frozen simulator. So the simulator was trained before, now it's frozen. Now it's the time to train the controller, but we want to do it in closed loop, so the controller needs to learn on its own how to do it. Okay. Any idea on how we can do that? How you would do it? Also from online, of course. There are different ways. Yeah, you can say what you think could be good options or possible options. Any ideas?
Sì, può
You can do it in many ways.
Yeah.
So one way that maybe some of you have in mind, of course, is reinforcement learning, a very powerful tool. So with reinforcement learning, we basically learn a policy for the controller by exploration. So we learn by trial and error, of course. But reinforcement learning is a very powerful tool. I mean, at the end, you can get a very good controller. The problem is it requires typically millions of interactions with the plant. So you can do it in simulation. Doing it in the real world is a bit tricky. I mean, online reinforcement learning is a very hard topic, let's say.
Commonly in the reinforcement learning, you have the possibility to exploit the gradient of the model commonly. Okay. So
yes, so typically in RL, you actually consider the plant as a
black box, and so the only possibility is try and see what's happened. But yeah, if you go probably in the next slide, probably you have the
so yes, the idea here can be, well, it's not something it's not something impossible, but let's reuse. So we have here the desired output, right? This is the desired output, and this is the predicted output. Our goal, if we don't use reinforcement learning, of course, our goal can be to try to bring the predicted output to be the same as the desired output, right? Ideally, this is what we would like to have. So our loss function can be built on minimizing the square the norm of y minus y hat. So we want to bring the square norm. Sorry, here I'm missing a square. But ideally, we want to bring y as close as possible to y hat. And in this way, okay, this is the loss function. But how do we actually train the model? Well, we can. This is an unsupervised loss, yeah. So it doesn't require us to collect data. Basically, if you have the simulator that is pre-trained, you don't need to collect other data. You're just essentially providing a set of desired output trajectories that can be computed by a planner if you have it. You still need to give them.
Of course, you need to create a set of desired trajectory that are visible to your system, of course. Otherwise, it's impossible.
Indeed. So this is indeed an unsupervised loss. And in this way, if we do this carefully, the controller can be trained end-to-end without actually going in the real world and without ground truth data. And the idea here is to backpropagate the loss L. We can backpropagate its gradients, nabla L, through the simulator, which is pre-trained, so we don't need to update it. And we backpropagate also through what we care about, which is the controller. And in particular, okay, this is called differentiable closed-loop controller training. Yeah, it's not something that we propose. It's something that is actually done in the community. We have been working on that also with Gaston and also in our lab in Munich. You can do this also with MPC, by the way. We have a recent example on how to do it with nonlinear MPC, with differentiable closed-loop controller training. But the idea is, okay, let's say the parameters of your controllers are theta. So your controller is parameterized by theta. Then you can use simple gradient descent, okay? So you update the parameters of theta with a simple gradient descent rule. So nabla L will be the gradient of your loss with respect to the trainable parameters theta. And eta here can be a learning rate, which of course can be variable. This is a very simple example. But the idea, yes, is that you can do gradient-based learning, for example, with Adam, with your favorite method, to do basically data-free, training and adaptation. So actually, the only data you need is the planning, the desired outputs, but you don't need to go and collect other data on the real system. And yes, and this is indeed a powerful technique. So this enables training, but also adaptation, because then if you know that the parameters of your simulation of your simulators are changing, then you can adapt to the corresponding policy for the controller by doing some steps of gradient adaptation. Basically, gradient-based learning is very fast, very, very quick. It doesn't require to compute hashes or whatever, so you can do it also online, especially on small batches of data. And and we also showed actually some examples of online learning. And so indeed, now we can.
And the other things that here is trained only on the next YK, but of course you can loop the controller, and you can create all the future window here, and so you can compare all the window with all the samples that your system will generate in the future. So you not make one single step, but you make a long prediction in the future and keep the controller learn to control all the trajectory your system. Okay, so in principle you can execute for a long horizon. Yeah.
Yes. We have actually an example of
A
this.
simple example.
Yeah, example. Do you prefer to see it now, or shall we take?
Yeah, well, maybe we can just.
You can take it. Yeah, of course. Yeah, question.
Know if like the simulator learns something wrong.
Yeah.
Like, since you're not using any new data, the
Yes.
controller of course.
Yes, you're right. You're right.
Yeah.
So the question is, what if the simulator is wrong here? And indeed, it's a good point. If the simulator is wrong, you're also learning somehow the wrong policy.
Yeah.
So
course.
in principle, this works as long as you have a good simulator. But there are also ways to do this. I mean, this is a more general technique. There's also ways to do it in the real world. In the real world, you don't have the simulator, or in principle, there are two ways to do it in the real world. Either you keep the simulator, but then you need to adapt the simulator as well with real world data. And then you fine-tune the controller with a gradient-based differentiable. Or there are also some people in the literature that are doing it in the real world, but without a simulator. So you don't have a simulator here, but there are actually ways to estimate the gradient. Even if you don't have the simulator, you can still estimate the gradient recursively by looking at the measurements that you have, y. And so you can still do that also in the real world.
Yeah, I want to say that if you apply this approach, but instead to use a model structured neural network, you use a general purpose neural network. You can in principle do this approach, but this commonly can be more dangerous because thanks to the fact that your network is commonly big and you cannot extrapolate so well, not physically, what can happen that your controller try find some strange way to control the system in a completely out of domain of your network. This can be dangerous if you have a more general neural networks. Okay. Instead, if you have a model structure, you are commonly more safe because the network is able to extrapolate in more a physical way. And so if the controller find some strange way to control the system to fit the data, not to fit the trajectory, commonly you not make a big mistake. Okay, so yeah, this is something that this approach is helped by the fact that you are doing structured networks. Yeah, I saw a work in ICRA where they have a model, okay, a model that was composed by a feed-forward network that was taking the residual, and the other was a differentiable model. So completely model based. Okay, so two branches as we saw residual learning, no? So black box plus model, no? They train this part of the model using a data, and then they put the model here and they try to train the controller. They said that instead to propagate the gradient through the model and through the residual, they avoid to backpropagate the gradient to the residual to avoid that problem, probably. Okay, so they prefer to backpropagate only through the physical model because the gradient of the physical model was already enough to learn the model, the controller. So for this reason, I empathize that the use of model structure in this framework, in this approach is more safe and is more reliable and yeah.
But let's say in general, if you have a good simulator, if you have a good model, this is a good way to actually give you a very good initial guess for your simulator. Then of course you should go in the real world and you will have some sim to real. So you still need to adapt in the real world, and you can do that by estimating the gradients, for example, as some people showed. Or, I mean, of course, this is just one part of the pipeline. So in general, you don't just have simulation and control, you also have planning and perception if you have a complete loop. And that's, if you want, this differentiable idea is applying to the whole framework. Yeah, so you can also then decide to adapt the planning module to optimize its interaction with the control and perception. Yeah, we're going in that direction also in my lab in two.
We are trying. Yes. The objective is try to fulfill the whole pipeline.
The whole pipeline, yes.
Yeah.
So indeed, there are many people now trying to do that. We think it's a powerful tool because we've also shown the comparison with reinforcement learning in our differentiable MPC paper, and there is basically one order of magnitude in sample efficiency. RL sometimes can still find better solutions than gradient-based, of course, because it's exploring more.
Yeah.
So with RL, you can still find better solutions, but you are way less sample efficient. Yeah, basically. Yes. But if you're interested, I can send you some papers on this topic. Yeah. Also the ones that estimate the gradients without having the physical model. And then also our works with Gastone, and also work with it in my lab, yes, too.
Okay. So
yeah,
we can take...
I think, yeah, maybe we'll start by looking at one example in this topic. Yeah, the example is in mass spring damper. It's very simple. Mass spring damper. Simple.
Yeah, I mean, this is the dynamics, simple dynamics of mass spring damper. We design, in the slide probably online you see, but here is a problem of the monitor that is shifted on the right side. Here you have the discrete dynamics of the mass spring damper. Okay, so you have the free response plus the force response. Modeled by two finite impulse response filter. Okay, these dynamics mimic the discrete dynamics of a mass spring damper. So in principle, is if you have this system, you can completely fit the data because this model is completely compliant with this. The only things that is different, this is in continuous time. This is in discrete time.
So in this case, it's a linear system. So the description with neural compositional modules is exact. Yeah,
exact.
Approximating, it's just an exact representation.
Yeah. So what you do here, first step, you take the dynamics learning of the direct model. So you have this neural mass spring damper, and what you do is just fitting the target. Okay, so the data that you extract from your in this case was a simulation or a simple example to show the idea of the design of the model, and then train the controller in loop. So in this first step, you take the prediction of your model, forward model, and you take the data, and then you compute the loss. You can do this in one single step, so one step prediction. So you predict only k plus 1, but in principle you can iterate your model for more step and predict a more long horizon. And then you take the model, you fix the data, and then you compose with the controller the learning for the inverse model using the pre-trained direct model. So in this case, yeah, you freeze the neural mass spring damper. You can see that there are two loops to make this simulation, because the first loop needs to predict the next by next, and so on, all the horizon, okay, and feed in the model. The second loop needs for the controller to compute the error. Here, the example was to train a PID controller. So the neural controller is just PID, where KP, KD, and KE are unknown. I want to just to design the proper value to minimize a specific loss that can be the same one. So I just want to follow a specific trajectory in the future. So the target, okay. And so I can do this. The error is here from the target to, the error is not anymore from the output of the neural model to the to the data set, but is with respect to a target. Okay, so I decide a step or constant or sinusoid, what I want, and I compare this target with the predicted value from the neural model, and then I train the neural controller. This was the fitting. I mean, as I said before, is exact because the model is completely equal to the system that I'm going to model, and this was the result of the PID. What you can do if you want to, for example, I don't want to have, for example, overshoot. I don't like to have an overshoot. So you can include, for example, a loss function that reduce the overshoot. Say, okay, if I go above the target, you can add an additional loss function to reduce this. And I don't have the result, but I compute in my PC and was good. So you can add an additional loss function and you get a different response of your PID. So you can adjust your parameter, you can adjust your loss function in order to fit what you want, okay? This I think is very nice. And here I don't have the result, but I compare this result with the result of, I don't know if you are familiar with MATLAB. In MATLAB, if you take a model in Simulink, you can, and you create a PID, you can click on MATLAB and you fine tune and you can make an automatic tuning of the PID thanks to the simulation. And the result was comparable to the fitting that I got in MATLAB. Probably when I decide a specific loss function, I got the same result.
Yeah, so for PIDs, we have also automatic tuning methods there.
Yeah.
But if you use a more complex controller...
Yeah, of course, this was just to verify that, yeah.
If you use an MPC or whatever as a controller on a neural network, then you cannot use MATLAB,
yeah.
Unfortunately.
No. This is general, but I want just to verify that the result in a simple case was satisfying. Okay, so maybe we can just show. Please.
Are the weights of the controller somehow related to the gains of the PID?
The gains of No, the controller here, this controller was a PID. Was exactly a PID dynamics. Okay, so was tuning KP, KD, and KE.
Okay.
Yeah.
It's neural controller that tunes the 3 gains.
Is the shape, the architecture of that neural network is a PID.
Okay.
Yeah.
So you can also inspect
Finally, I get KP, KD, and KE, and I verify that was very similar to the one that I obtained with MATLAB.
Okay.
Yeah. It's not a general purpose control.
Purpose.
No, it's exactly the same structure. So it was a PID neural controller. So neural because I'm just I tune the parameter using backpropagation. I can say that is a PID tuned by backpropagation.
Okay.
Yeah. In general, of course, the approach can be applied with a different control.
The neural control are pre-trainable parameters.
Yeah, pre-trainable parameter. Just pre-trainable.
Okay.
Yeah. But the objective was to see if the three parameters were similar to the auto-tune of MATLAB. So
it's more a proof of concept.
Yeah.
Then you can of course apply your own more complex controller. But we just wanted to have a toy example also to show here. Yes.
We open the code.
We can show briefly.
Here the code is very compact and it's nice to see the closed loops. That is something that probably in PyTorch is not very easy. I mean, to implement this kind of loops and to propagate the dynamics for long horizon. But here is so
this
one
is the
single line
model.
is the model. So you see the sum of the two finite inputs response, and then I create the estimator, and I create a target variable for training the model. Okay, so I neuralize the model, and then I load the data and I train the model. Okay, so simple.
So this is just the training of the direct model, of the simulation model of the mass spring damper.
Yeah.
And
no, the controller was up. So okay.
And then we have the controller here.
Yeah, probably here we have both.
Here you have both. Okay.
Yeah.
So here
it's the same. Okay, mass spring. Yeah, it's written in a different way, but it's the same X3, X4, so the two component of the model. We model, there is the target variable again here. Then we neuralize the model.
This is the time step for the
here was the data set was sampled in a different from before. Okay, so then we extract the data and we train the model. Okay, and then we visualize. There are some visualization steps that you can use. Here I perform. Here an example. I perform the training not only in feed forward. Okay, the first training here. Okay, here we just set epochs, number of the dimension of batch, learning rate, how I split the data set. Okay. But in the second part, we train also the model in loop. So the x that we predict, the xn, this is the variable that I predict, is feed inside the value of x.
Yeah, so it's basically this training loop,
I'm
right?
training this in feedback. Okay, so this
is a closed loop.
Just to refine the output. Okay, just to refine to have a very, very precise. If you see, if you go back, in the plot, after the next, after the feedback training, it's very, very completely correlated. So it's because with the one single step, maybe you will not have this exact matching, but the objective was to get the exact matching. So I train also in feedback to refine, and I reduce the learning rate when I do in feedback, because of course I take a more long horizon, so I do want to reduce the
because this can also drive into instability, right? If
you
do
when you
closed
do
loop
for a
training,
long horizon, you see prediction sample is 1,500 steps. So for a very, very long horizon.
So you basically integrate forward in closed loop, the dynamics for a lot of time, and then you risk having instability if you do it in closed loop. So we need to be careful with the learning rate and be low enough to prevent large destabilizing updates of the parameters.
Of course, for this reason I make first of all the standard training in one single step. Now, so after you adjust the weights, you can try to predict for a long horizon, and you get a good matching. Okay, so then we train this, and then I see, as I mentioned before, I create this PID. Okay, so just PID controller. Okay, simple PID controller. I compute the error between the target and the measurement variable. Okay, and here is nice because we implement a easy way to integrate and differentiate the error variable. Okay, so the operation of integration and the derivation are computed inside the framework. And then you create the controller. So you have now two model. One is the mass spring damper.
So you have another add model here, right? This is the neural mass spring damper. So this is the simulator, and then you have on the same objective, on the same instantiation of the object, you have another add model here. Yes. which are the
Okay.
controller.
So we had the two controllers, the two models, okay, and then you serialize at that moment you serialize both component, and then you can connect the port from one to the other. So F,
So
yeah.
basically,
So we needed to
yes.
connect the output of the controller to the input of the neural model. We need to connect, this. Okay, so we connect the F PID, that is the F output from the PID to the F that was the input of the model. And then we need to create two closed loop, one to close loop the dynamics of this closed loop here, and the other one is the from the measure is the output of
this one,
from the model to the controller to compute the error.
Yes.
And this is done by this during the training phase. So the model are still disconnected, but during the training I decide to train together in this architecture, in this composition.
So indeed, up to now they are disconnected, but then in the training function you say how they are connected, what is closed loop on what, and you can specify the connections. Yes. And I think these strings need to be the same as the ones you define, right?
The names must matching. Yeah.
So here we said the output of the PID is called FPID. It's a force, and so you want to connect then the force that is taken as input by the direct model with the force taken as output by the PID. So the names of the strings here must match, with what you defined before.
Yeah.
Okay, and then yes, you want to basically do everything for 500 steps. After 500 steps, you basically backpropagate, right?
I propagate for 400 steps, and then I cancel the memory and I start for another 500.
So we just integrate forward. So use the controller, feed the output to the model for 500 steps, time steps. The time step is 0.1. I think the one we defined before, 0.01.
Yeah.
So basically for 5 seconds we do this, and then we reset
the memory,
the initial state, the memory, everything starts again. Yes.
And here I was plotting the parameters. What I want? No, it go up. I want to see one thing. No, okay. Here I used for training the controller. For training the controller, I use the same data set as we generate for training the model. But in principle, you can use a different data set. This is what you want, up to you. And then in the last part of the code, I just test my controller on some targets that are constant targets that you want. They are the one I show in the
And in this case, the model is not frozen, right?
No, the model is frozen. No.
The model is frozen.
Yeah.
Right?
You said.
Okay. Where I said here. I say go down. This I train the model. Here. Models. PID.
So you specify only the models that you want to train.
Yeah.
So this is the name of the model, right? Because here we have add model, PID, it's called, this is the name of the model. So here we have to say which models are actually trainable.
Yeah.
It's only the PID. Yeah. The other model was called neural mass spring damper, but it's not in the names. Yeah. If we want to train that one as well, we have to have a list probably here on a dictionary.
If you remove the list, you train all the models. Otherwise, you train just the PID. This is a simple way to say I want to train this part of the network. Commonly in PyTorch, what you need to do is select all the parameters that are the model and say this parameter for that training are frozen. No.
Yes.
Here you just need to say, okay, this model is what I want to do.
In the optimizer.
In the optimizer in PyTorch, you say, I want to freeze these parameters. You obtain the same result. Yeah. Here, the idea of composition models is the idea to say, okay, I want to train this component, or I want to train this, and
Yeah, so you can in one shot unfreeze or freeze the parameters of a whole model, which could have in principle hundreds of parameters. Yeah, so you don't need to go and manually say which are trainable and which not. You can do everything in one shot with this code. Yeah.
And the other parameters of the training come from these defaults that were defined at the beginning, probably.
Yes, the number of epochs, batch size, learning rate,
and then you
so on. Yeah.
Okay.
Good. Yeah, I think we said everything for this example, right? Okay.
Yeah, the most interesting part here was
Okay.
here.
Yeah, so basically, okay, they can still see, yes. So basically, yeah, and Nodally can actually be used also beyond model structure neural networks.
We make two examples. I don't know if you are interested to have a look. I did some simple nonlinear fitting. I try to implement a sublet learning, and the last one, I implement one example that was in the paper Physics Informed Neural Networks.
It's
I
probably
think
the one.
yeah, we can. I want to show you just an example of the Physics Informed, how I implemented the Physics Informed inside the framework, and the final result that are the same.
The Burger's equation, yeah.
Equation.
Yes, this is another example that was in the Raisi's paper that we've seen during the PINS lecture.
Yeah. So in the Burger equation, in that example, they create a fully connected layer. So I just stack the same amount of parameter that they mention in the paper. So here I just create a loop to make a fully connected structure.
Yes,
there is not yet a simple way to say MPL and the number of layers, but
so this is just the neural network that approximates the states. Yeah, so the states are xt. So the solution basically, you want to approximate or learn the solution with a general purpose neural network, in this case, as they do in the paper.
Yeah.
The solution is XT. Yeah.
And the output of the output of the network is U. The final layer. The final layer is was called U in the. If you open the paper, maybe we can just compare that. I think I use the same. No. If you can click from the code at the beginning. Yeah, you have the download. You can download from here. I think it's faster.
Yes, this is the paper by Raisi, in which they show the example. This is the Schrödinger, the one we've seen during the course. Navier-Stokes.
Not one. It's not this.
But yeah, you find it.
This one.
Quarter. No, it's somewhere.
No, it's down the Burgers.
But in any case, yeah, you find it.
Yeah, because there is the plot.
This one probably, yes.
Okay.
So the solution is called U. Yeah, the U is the solution you want to find.
And here you are computing the derivative of time with respect to the time of U.
Yes.
U by the derivative of U with respect to X, and then the double derivative of U with respect to X.
Yes.
And if you go in the code, okay, here you have differentiate. Okay, so you see I differentiate U with respect to the time. Okay.
Yes, which is this one, yeah.
The first one.
And then you have U times the derivative.
U by the derivative of U with respect to the X, and the last part is 0.01 divided by pi.
Yeah.
Differentiate. Yeah, there is no simple way to make double differentiation, but yeah, you can call 2 times U by X.
Okay, and that's the equation that you want to solve basically.
Then you generate the two output. Okay, one is the F and the other one is U. Okay,
F is the
output of your neural network, and F is the output of the function that you want to
Yes,
use
so
as
F is the one we want to drive to 0 because we want to satisfy the equation exactly, because the equation needs to be equal to 0. And U instead is the solution we want to find, yeah.
Yeah. So I defined the two.
Which is computed with a neural network. Yes.
Yeah, I create the target and the bound. So are two inputs that I'm using for the training.
But do we have also U target here? We have the
yeah, for the boundary, for the
boundary.
for the initial condition.
For the initial conditions, yes.
Then I create the minimization inside in the bound and in the bound and F in and I put F to 0. Okay, so
yes, so F needs to be driven to 0. While U needs to be driven to its boundary conditions, okay, yeah. Which are probably expressed by this one.
Yeah, and then you go and you can just show the result here and create the data set. And then there is the plot down that are the, yeah. Here is the initial condition, okay? This is the initial condition of the system.
At time t equals 0, yes.
Equals 0, and then if you go down...
So the initial condition is basically satisfied, yeah, with some deviation.
Yeah,
but...
smaller deviation. And here you have the at different time you get this result, and then there is the 3D plot. Yeah, this is the boundary. Okay, you see it's 0 minus 0.06, so it's must. I mean, the target was completely 0, but are not.
Yeah, here the values are small. Yes,
small, and finally, yeah, this is the shape you get. And if you look at the paper, if you show. Yeah, here you have
something. Yeah, it's something similar. Yeah, qualitatively similar. Yeah. So the function U depends on both X and T.
We are doing completely the same operation. Yeah.
Yes.
It's a matter of probably the initial condition to get us. I mean, it was completely the same. Yeah.
Okay.
Okay. Yeah.
Yes. Questions here on the pin example? Also from online, of course.
I mean, here the objective was to make very easy to differentiate with your network with respect to.
Yes. You see, at the end, the definition of the network is here, is in like 10, 12 lines, yeah? Mm-hmm. I mean, the rest is post-processing and stuff.
So we not have yet a simple way to create a model, a multi-layer perceptron.
Yes,
because I mean, this is not the objective of the framework to create a model.
Yes.
Multi-layer perceptron.
So we have a stack of a linear layer at an H, another linear, but basically it's a multi-layer perceptron to approximate the solution U. And then basically a simple way to write the PDE, the partial differential equation, and that's done, yeah. So with differentiate, you can also differentiate with respect to a partial variable, yeah. So it doesn't need to be the total derivative; it can also be the partial.
Derivative, if you put just differentiate with respect to U, you obtain the total derivative in time. Okay. Otherwise, you can make a partial derivative.
Okay, right. If there is no question, we can see quickly some conclusions about the course. So, by the way, in the repository, Nodally applications, you find also other examples. Also equation learning, so equation discovery, inverted pendulum, other things. We are also happy to prepare other applications, maybe if you're interested, also for your I mean, as a continuation of the report, you're probably going to write if you want the credits. We're very pleased to prepare new applications, then also possibly make them open source if your project allows in the repository, or in any case, work on other applications. So yes, we can then move to some outlook and future directions just to conclude the course. I think you're still seeing everything. Yes. Okay, so indeed, some outlook and future directions in some trendy fields, let's say. For example, generative foundation models. We mentioned them in the first lecture of the course. We said, yes, they are indeed increasingly popular. We are also using them quite a lot in our lab in TUM. What we are also trying to do is indeed to try to inject some physics priors inside them. There are very few examples. Of course, the generative foundation models, I mean LLMs, visual language models, world models, video generation models. There are a few examples that try to combine physics. In principle, it's possible, right? They are also a form of neural networks and machine learning, but very few examples up to now. But if you go to conferences, everybody wants to do that. Yeah, if you go to IPRO, everybody says, oh yeah, very cool, I want to do physics-informed foundation models. Yeah, but then maybe a few people know how to do it, but the community is very interested in that. And yes, especially for embodied AI with physical systems, we have the problem of data, we said. So physics can fill the data gap, or at least give you some good intuition to generalize beyond what you can see with the data. Yes, exactly. And so basically, in principle, you can inject physics wherever you want, also with foundation models. We can see an example from our lab in a paper we did this year. We're going to submit it soon. So these are some preliminary examples in which we were injecting physics in the loss function, so physics-informed foundation models. In this case, it was a vision language action model. So we do vision-based semantic reasoning for trajectory planning in autonomous driving. So basically, we have our VLA, okay, a vision language action model. And basically, we query the model, which is used for autonomous driving at the end. So we query the model, we tell the model, please generate sporty driving trajectories. So I want to drive sporty today. And basically what we need to feed to the model is the initial states of the car, so where we are right now. And not only right now, also our past history, again, can be important for the to understand what's actually the current state of the system, right? So also 0.5 seconds in the past for the positions and velocities and accelerations. The goal state, where we want to go at the end of our planning horizon, the XY position at the end of our horizon. And then it's a vision model, right? A vision language action. So we can also feed the model with an image of the current scenario. Actually, we need to feed the model with an image of the current scenario. It can be in the form of a bird's eye view, BEV, or first-person view. So this is a BEV, basically. So a bird's eye view of the scenario from the top, or a first-person view in which we are driving. By the way, we did this in the Carla simulator. So it's a 3D high-fidelity simulator for vehicles, autonomous driving, very popular in the community. Yes, so basically this is, for example, what you see in Carla, right? So you see the vehicle driving. And the VLA, actually our foundation model, outputs the trajectory. So XY, orientation, theta, velocity, and acceleration for the car for the next 3 seconds in our application, right? So you can think, okay, maybe you have in mind some alternative ways to do that, like MPC or graph-based planners, whatever. Here we're using a vision-based planner to perform basically semantic reasoning. So from an image, we need to understand what's the context, where are the other cars, the other agents, pedestrians, and what is our trajectory to drive to the goal, considering our context. And indeed, yeah, in this case, we use a VLA, an open source VLA, which is quite a big model. I mean, they are foundation models, meaning that they are big models pre-trained with internet scale data. So here the LLM backbone that we have is pre-trained with the internet scale data. And it's a model from the Qwen family with 4 billion parameters, yeah, so way more than the model structure, of course, neural networks which we've seen so far. Here we're talking about billions of parameters, yeah, so a lot of orders of magnitude more. But it's what you need if you want to really go with internet scale data, right? With LLMs. So basically we have an LLM backbone, but then we have a vision encoder, a vision encoder here that encodes the input images. And then we have a text tokenizer, so that takes as input our textual prompt, for example, drive sporty or drive carefully. So that takes into account the driving style. Yeah, here we call this model style VLA because we want to drive with our own driving styles. And basically, yes, we fine-tuned the model. We cannot afford retraining the full LLM because we would need the servers of NVIDIA probably, or I mean, a lot of H100s and so on. So basically, we need to selectively fine-tune some parts of the model on the hardware we have available, like a 4090 or 5090 GPU. And so we decided to fine-tune the vision encoder and also to fine-tune selectively some components in the LLM, some basically lightweight adapter matrices. It's called the LoRa, what people call LoRa, so low rank adaptation. We're not retraining the full LLM, but just some adaptation matrices to correct the output of the LLM and the outputs of the attention mechanisms. And we also fine-tune a decoder at the end, a multi-layer perceptron decoder that extracts from the LLM the trajectories and then uses them to compute a certain loss function. We're going to see that this loss function will also contain some physics-informed components. Indeed, so in the design of the loss function, we have a mix of cross-entropy loss. Yeah, this is something that I'm not going to explain, but it's what people use to fine-tune LLMs, basically, based on a probabilistic description of their output, based on their past history of inputs. But on top of the cross-entropy loss, we also use a physics-informed loss that in this case is a kinematics informed, a kinematic consistency loss. We call it PIKC, which is a physics-informed kinematic consistency loss, in which basically we want to reuse some kinematic predictions, X and Y, based on what our model predicted at the last time step. So basically X, Y, the model was already outputting X, Y, velocity, orientation, acceleration A at the past time step. Okay, let's use the kinematic laws that we write here, very simple kinematic laws, to compute the predictions based on the past time step. Yeah, so based on the past time step, we know if we integrate forward, we know the predicted position X, Y. Again, yeah, based on the kinematics. And we can let our model in the loss function, we can minimize the deviations between the kinematic prediction and the real model output XY at the next time step t+1. So this is a form of physics-informed loss function, if you want, a very simple one. We're not imposing, well, it's a differential equation if you want, but it's very simple, like we're integrating a very simple equation. But this can still be effective, right? So it's an unsupervised physics loss, and then we have our supervised, partly supervised loss with the rest of the terms. And basically, yeah, we're comparing with our mixed loss function and our fine-tuning. We're comparing the outputs of proprietary models like AlphaMayo, maybe you know from NVIDIA, very popular one, open source, but also proprietary models like Gemini 3 Pro. So our model is the style VLA, is the third one. Then we have, well, yeah, the second one. Then we have the ground truth in blue. And then we have our goal. So we know we want to go there at the end of the horizon. It's the green star. Our model is outputting the red trajectory, very close to the ground truth. Some models you see are totally off. Yeah. So for example, SimLingo is totally off. AlphaMayo is somehow good, but maybe needs some fine-tuning. So we only fine-tune our own model. The others are zero-shot deployed because they are conceived to be zero-shot. Yeah, they are foundation models. So they should be used zero-shot in principle. But you see, yeah, our model at the end, at least with the fine tuning, with the physics informed loss, cannot perform all the models, all the benchmarks on a set of metrics, yeah, like average displacement error, ADE, or final displacement error, FDE. Yeah, this is the impact of the dataset size at the beginning. So the first part of the table is the dataset size. So if we use a small, medium, large, or standard, very large actually, dataset with 50K examples, and you see the impact of data is clear for foundation models. The more, the better. Okay, so the larger the dataset size for fine tuning, the better the model will be performing on unseen data. So these are then unseen. The metrics are on never seen data. The impact of the loss components, yeah, if you use the PIKC, so the physics informed kinematic consistency, you obtain the best performance in this case, with respect to not using it, with respect to using only the cross entropy and the regularization loss. So you see, even if the model is super big, like vision language, 4 billion parameters, people say forget about physics, just use data, it will solve the problem. Actually, if you think of embedding some also very, very basic physics, yeah, kinematics or simple dynamics, it still helps. Even if the model is huge, it helps. So yeah, this I would like also to be a take-home message that for you, I mean, your research, I think it's a nice way. There are also some examples with foundation models that try to inject these priors. I think in the next year, a couple of years, we're going to see an explosion of these examples. So it's also a nice moment to work on these topics, I would say. And yeah, okay, questions on this one? Otherwise, yeah, we can also briefly say what are the future directions, promising future directions. Of course, there are a set of future directions, but some of them to address open challenges. So, of course, in the course, we mentioned about 3 categories, yeah, physics guided, encoded, informed machine learning, depending on where you put the physics priors. But an interesting future direction, we think, is combining them. Because in principle, they offer 3 principled ways of injecting physics. People should think of combining them together. Yes, so this can be a promising direction. And of course, foundation models, yeah, the trend is there for foundation models, but using physics priors to fill the data gap is still an open problem. People don't know, don't have a recipe for that yet, but we are trying to explore some recipes. Differentiable end-to-end training, yeah, this is related to physics-informed machine learning. It's what we've seen today with the end-to-end controller training. It's also a promising direction because it lets you boosting the performance of a controller, for example, without using data, actually, without using real-world data, and also perform a rapid adaptation if the conditions change online. So yes, and then we always need to adapt, especially if we have physical systems in the wild. In the real world, we need to always adapt online for the whole life of our physical system. We have to do it in a data efficient way, possibly also in a physics aware way. So if we know what's changing, we can also selectively adapt some components of the machine learning models. And of course, safety. Yeah, safety is always an issue. We need to possibly prove that our system is safe, is verifiable, so its performance can be somehow certified. Yeah, there are people working on verifiability and safety, but especially if you think of foundation models, this is particularly tricky, right? Proving safety and verifiability. But the thing is, the world is evolving in this direction. We need to acknowledge that, right? So foundation models are becoming a reality, so we need also to somehow prove their safety and their operation. Yes, and finally interpretability. Yeah, it's always important to understand what's going on in the system. Sometimes with black box models, it's tricky to do that, but we need to somehow explain what's going on, also to let the public understand and increase their acceptance of what we do. Right? Yeah, then do you have other points here as future directions? I think there are many. This is just a short list, yeah? Other things that come to your mind, maybe based on your own research, yeah, with the challenges you are facing right now. So of course, and then there are domain-specific challenges, I think, yeah, and that we should list, but depending on the system, yeah, there are many. So with this, we would like to thank you for attending the course. Just remember, okay, for those of you who want to have the credits recognized at the end and that need to have the credits associated with the final exam, then please send us your report by the end of August. We're actually happy to support you. So if you have maybe a preliminary idea, you want to speak to us before writing the report, that's fine.
Yeah.
We can arrange a meeting online or in person if I'm here sometimes, but online, of course, goes. We can discuss maybe your research idea, give you some insights, how this can be new enough to the community, what we could do, and then you can write the report. So we're happy to do that. If instead you don't need the final exam, but you still want to have the certificate, we will create an Excel file in the shared Google Drive repository. I will maybe write an email when this is out. And please write your name there and write if you want to have the credits for the report, with the report or without the report, so we know. So please do not send us email for this. Just write in the Excel file that we will create. So we know if we need to expect from you the report by the end of August, or if we can just write your name to the secretary here in Trento, and they will prepare the certificate for you in any case. In any case, you will have the certificate with or without the final exam. And okay, final thing, we would also like to have your feedback. It would be really appreciated. So we are preparing a short questionnaire. It's not online yet, but I will send you the email. Just 5 minutes. It would be really appreciated because next year we want to do to prepare the course again, maybe with improvements based on your comments. So it would be really helpful. And okay, for final thing, this is an advertisement for the work we do. Yeah, we have at TUM and also here in Trento. So we have also in our lab in Munich. Yeah, it's the Autonomous Vehicle Systems Lab. We have a lot of robots. Yeah, we work on mobile robotics, but the methods are the ones we presented. Yeah, so at the intersection of optimization, machine learning, control, modeling. Yeah, we have the full-scale cars, we have the humanoids now, we have the wheeled quadrupeds, we have the small-scale cars, the full-scale cars, quite a lot. Yeah. So you can enjoy, and I mean, we're also very open to have visiting students to collaborate with us, visiting PhD students as well. So please feel free if you at least if you work in somehow in mobile robotics, that would be preferable, but the methods are the ones we discussed. Yeah, I mean, maybe whatever at the intersection of learning, planning, control, optimization, with a possible application on these systems. Yeah. Yes. So many thanks for attending, and of course, if you have questions.
Yeah. Also for me,
yes.
That I'm working here, we have some hardware also. So if you are curious to use, we have also 2 quadrupeds and some small vehicles. And also I'm open to try to include different fields in my research project that is applying model structure or at least in general, model-based approach and data-driven, so merge these two different way to approach a problem. Yeah, and so yeah, if you want to try and you want to come speak with us, we are open to enjoy a
Indeed, yeah,
conversation.
indeed.
Yeah,
So
yeah.
with Gastone, we're open
Yeah.
to all the fields, of course,
Yeah.
of physical systems. Yeah. For us in Munich, we're a bit more restricted to mobile robotics, but here with Gastone, I think we can really explore also other physical systems by combining machine learning and physics. Yes. Yes.
Also, we can support you because we have a big group. So yeah.
Indeed, yes. The group of Gastone is expanding. I think you have already how many PhDs?
Yeah, now we are 6.
6 PhDs, yeah, some research assistants, 2 postdocs,
Yeah.
so also quite a big group. Yes.
Thank you.
Thank you. Yeah,
thank you
thank you for
again.
attending, and we're